If you had a hard time multiplying and dividing expressions with exponents, you may want to go back and review that section first before getting started. In this first example, we are multiplying like bases. So that means we need to add our exponents. So we have 12 to the 1/8 plus 5/6 power. So we have to think way back when about how do we add fractions. We need to get a common denominator. So our common denominator here is going to be 24. We're looking for the least common denominator that we can come up with. In order to get 24 from 8, I had to multiply by 3, so I multiply its numerator by 3 as well. If I need to multiply 6 times 4 to get 24, then I need to multiply 5 times 4 as well, and I get 20. So we get 12 to the 23 over 24 power. The next example, it's kind of like having x to some power times y to some power, then raised to another power. We then can't simplify anything with the 5 and the 7 in there, but we can deal with them individually. So 5 to the 1/3 times 3 power times 7 to the 1/4 times 3 power. 1/3 of 3 is just 1, so we get a 5. 1/4 of 3, we get 3/4. So 5 times 7 to the 3/4 power is our final answer there. In the next one, if you recognize that 4 is a power of 2, it's definitely going to help you here because 4 is really 2 squared. Then we have that raised to the 6th power. So inside, we really have 2 to the 6th times 2 squared, then raised to the 6th power. All of that being raised to the negative 1/6 power. So 2 to the 6th times 2 to the 12th, all then raised to the negative 1/6 power. This then is going to leave us with 2 to the 18th, then raised to the negative 1/6 power, or 2, I have to multiply my exponents, I get a negative 3. Negative exponents drop it down to the bottom, so 1 over 2 to the 3rd. And some of you are going to start skipping steps, and I get that, but I'm making sure to put everything in here so you can see exactly what's happening. And then with this one we can simplify, so we get 1 over 8. So 10 to the 2/5 on the bottom is like taking the exponent of 1 on the top minus the 2/5 power, while 1 is really 5/5 minus 2/5, we get 3/5 for our new exponent. So we have 10 to the 3/5 power. For the next example, 56 to the 1/4 and 7 to the 1/4, because our powers are the same, we can actually do the division first. So 56 divided by 7 is 8. We leave that to the 1/4 power and then raise it to the 5th power. When we have a power of a power, we multiply our exponents. So our final answer, 8 to the 5/4 power. Similar to what we did when the index, the n value, was just a 2, a square root. We didn't see the 2 there because it's the most common radical that we're going to use. But if we have an index of 3 or more, then you're going to see that number sitting perched up on the radical symbol. So here we've got the cube root of 125 times the cube root of 8. Well, that's the same thing as the cube root of 8 times 125, or 1,000. But what times itself, then times itself again? In other words, what cubed gives us 1,000? And our answer here would be 10. For the next one, we can actually, since we have the same radicals, really this is like saying 96 to the 1/5 power and 3 to the 1/5. So like on the previous problem where we had the same exponent but different bases, we could actually divide the numbers. Same sort of idea happens here, where we can divide to get the 5th root of 32. And the nice thing here is that there is a 5th root of 32, and that is 2. So we always want to make sure that our answer is left in simplest form. And just like we could break apart square roots, we can break apart any nth radical that we're dealing with. So if we have the cube root, we can break this into a perfect cube of something. So what perfect cube on your list goes into 104? And after looking at that for a minute, hopefully you realize that 8 does, and 8 is on your perfect cube list. And it's really 8 times 13, so it's really the cube root of 8 times the cube root of 13 would give us the cube root of 104. But the cube root of 8 is 2, so we get 2 times the cube root of 13. And in the next one, we have fourth roots that we're taking. So if I'm trying to take the fourth root of 27, but 27 is not on my perfect fourths list. So we can rationalize the denominator like we did earlier on in the year. If we had something like the square root of 3 in a denominator, we multiply both the top and the bottom by the square root of 3. Because the square root of 3 times square root of 3 broke that out on the bottom and gave us just a 3. Well, the reason that that happens is because the square root of 3 times 3 is really the square root of 3 squared. And these two things, the square root and the squared, undo each other and break that 3 free. So how many more powers of something? This is really 3 cubed. The 27 is really 3 cubed. So I'm going to need one more power of 3 in order to get a perfect fourth root. That would give me a 3 to the fourth power. So I'm actually going to multiply by the fourth root of 3 on both the top and the bottom. That's going to give us a fourth root of 30 on the top and the fourth root of 81 on the bottom. But 81 is really 3 to the fourth power. So if I want the fourth root of something to the fourth power, just take out that number on the inside. So we have the fourth root of 30 over 3. Like radicals have the same index and the same radicand. Essentially, if they look exactly the same, we can treat them like variables. Here we have a 7 times the fifth root of 12 minus the fifth root of 12. Well, there's really a 1 in front of here. So it's like saying 7x minus 1x. We get 6 times the fifth root of 12. In the next one, we see a 9 to the 2/3 power in each of these setups. So it's like saying 4x plus 8x. We end up with 12x, essentially. So 12 times 9 to the 2/3 power. And 9 to the 2/3 power, we can't simplify that. That would be like saying, take the 9, square it, then take the cube root, and that's not going to work out perfectly, so we just leave it as it is. In the next one, we really have here the cube root of 27 times the cube root of 3. That's really what the cube root of 81 breaks down into. So let's simplify that. The cube root of 27, that should be on your perfect cube list because that's 3 cubed. So we have 3 times the cube root of 3. And if you look at 24, 24 can be broken down as well into the cube root of 8 times the cube root of 3. So cube root of 8 is 2. We're left with the cube root of 3 attached to it. And now we can simplify. 3 times the cube root of 3 minus 2 times the cube root of 3 is going to leave us with 1 times the cube root of 3, or just the cube root of 3.